Welcome to a lesson on performing least squares linear regression using matrices. If we're given points as labeled here, the least squares regression line can be given by f of x equals b plus mx, where b would be the y-intercept and m would be the slope of the line, and this will minimize the sum of these squared errors, which are the errors in using the regression function f of x to estimate the true y values. So E sub I would be the error or the difference between the true y value and the function value from the line. And if we square all these errors, we have the sum of these squared errors. Let's see if we can set this up as a system of equations and then solve using matrices. Every given point would create a linear equation in the form of y sub n, the given y value, must equal b plus m times x sub n, plus e sub n, where again b is the y-intercept, m is the slope, x is the given x value, and then this e here on the end is the small error that we would have by using the regression line to make the prediction for the true y value. So again, each point creates a linear equation, and together we have a system of equations which we can write as a matrix equation. To do this, we start with forming matrix Y, which contains the given y values. Matrix X will have two columns, a column of 1s and then a column of the given x values. Matrix A will contain the y-intercept and slope, and matrix E will contain all of the errors. This gives us the matrix equation y equals x times A plus E. Our goal is to solve this equation for A, but before we do this, let's see why these 1s here are necessary. If we were to start multiplying matrix X and matrix A, row 1 times column 1, 1 times B gives us B, our y-intercept, and x sub 1 times m gives us the slope times the variable x. So this 1 is what gives us the y-intercept in each of these linear equations. Now we're not going to derive these formulas here, but to solve this matrix equation, A, remember that gives us the y-intercept and slope, is equal to this product here, where we have the inverse of the product of the transpose of matrix X and matrix X times the product of the transpose of matrix X and matrix Y. And the sum of these squared errors is equal to the transpose of matrix E times matrix E. Let's take a look at an example. We want to determine the least squares regression line from the given data, where X is the price in dollars and Y is the demand in monthly sales. We can see from the graph of the data, a linear regression line is going to be a pretty good fit for this data. Let's start by setting up our matrices. We want to start by setting up matrix Y and matrix X. Matrix Y is the column matrix with the given Y values, so it's a 5 by 1 matrix. Matrix X will be a 5 by 2 matrix because remember the first column will consist of 1s, the second column will consist of the given x values. So given these two matrices, we have the matrix equation y equals a times x plus e. We won't be able to find matrix E until after we solve for matrix A and then determine the errors using the regression line. So now we're going to find this product here, but we're going to do it in pieces. We're going to start by finding the product of the transpose of matrix X and matrix X. Well, here's matrix X. Notice how, again, it's a 5 by 2 matrix. So the transpose is going to be a 2 by 5 matrix. So this first column becomes row 1. The second column becomes row 2. Notice matrix X is a 5 by 2 matrix. The 5s tell us that we can perform the multiplication. The 2s tell us the dimension of our product. It's a 2 by 2 matrix, which I've already found to save some time. Now for the next step, we'll find the inverse of this product. Because this product is a 2 by 2 matrix, remember we can take the shortcut or use this formula here to find the inverse of our matrix, which again I've already done here. So for the next step, we want to find the product of the transpose of matrix X and matrix Y. We already found the transpose of matrix X earlier. Here's matrix Y. Again, notice how this is a 2 by 5 matrix. This is a 5 by 1 matrix. So the product is going to be a 2 by 1 matrix, which we see here. Again, I've already found this product due to time. Now that we have all the pieces, we can finally find matrix A, which again will give us the y-intercept and slope of our regression line. So matrix A is equal to the inverse of this product, which we have here, times this product, which we have here. This gives us a 2 by 1 matrix where the elements are approximately 211 and negative 1.7. So 211 is B, or the y-intercept of our regression line, and negative 1.7 is the slope of our regression line. So we have f of x equals 211 minus 1.7x. Or if we want to put this in slope-intercept form, we could say f of x equals negative 1.7x plus 211. Here's a graph of our line over the data. You can see that the line does fit the data pretty well, so it is a good model for the data. Now we're also asked to find the sum of the squares of the errors. So to do this, I recommend creating a table similar to this, where the first column is the given x values, the second column is the given y values. This third column here are the y values or function values from the regression equation, f of x equals 211 minus 1.7x. So the difference between y sub I and f of x sub I is the error, which we see here in the third column, which we need to form matrix E to find the sum of the squares of the errors. So to find the sum of the squares of the errors, we have the transpose of matrix E times matrix E. Notice how matrix E is a column matrix, the transpose is a row matrix, and this product is equal to 207.65, which is the sum of the square of the errors. Let's finish by taking a look at a question. Using our regression function or regression line, we want to know what the meaning of the slope is, and also we want to predict the demand if the price is set at $54. Well, the slope is the ratio of the change of y to the change of x. In this case, y is demand, so our slope represents the ratio of change of demand to change of x, which is change in price. Next, our slope is negative 1.7, which as a ratio would be negative 1.7 over 1. So the positive 1 represents an increase in price of $1, and the negative 1.7 represents a decrease of 1.7 in demand. So to put this in a sentence, according to the model, if the price increases by $1, we can expect a decrease in demand of 1.7 units per month. Next, we're asked to predict the demand if the price is set at $54. Well, x represents the price in dollars, so for the second part, we want to determine the function value at x equals 54. f of 54 is equal to 211 minus 1.7 times 54, which is equal to 211 minus 91.8, which would be 119.2. So according to the model, if the price is $54, we can expect a monthly demand of approximately 119 units. Okay, I think we'll go ahead and stop here. I hope you found this helpful.